This lecture will cover Chapter 6 of your textbook on deterministic planning. And this week, we're shifting from search in general, as we've been learning about, to a more structured form of decision-making called deterministic planning. By the end of this lecture, you should be able to explain the model of deterministic planning and represent actions using the strips formalism, which is one of the foundational representations in classical AI planning. You should also be able to compare forward and regression planning, describe how planning can be encoded as a constraint satisfaction problem, and relate deterministic planning to automated cyber response systems. So in other words, we're moving from exploring state spaces to deliberately constructing sequences of actions that achieve specific goals under known conditions. Let me get this into slideshow format for you. Now, classical planning makes a number of strong assumptions. The world is deterministic, meaning actions have predictable outcomes. The environment is fully observable, so the agent knows exactly what state it is in. Time progresses in discrete steps, and we are typically working with a single agent acting offline, meaning it reasons first and executes afterwards. These assumptions simplify the problem significantly. They remove uncertainty. They remove hidden variables. They remove randomness. And what remains is structured logical action selection. That may sound restrictive, but in many cybersecurity contexts, especially in automation and playbook execution, these assumptions actually hold surprisingly well. Now, planning in its simplest form is deciding what to do based on an agent's abilities, its goals, and the current state of the world. Under deterministic planning assumptions, there are no unexpected external events changing the environment behind the agent's back. The agent knows its state, and goals are defined as properties that must be true of some future state. So the planning problem becomes this. Given an initial state, a set of actions with known effects, and a goal condition, find a sequence of actions that leads from the initial state to a goal state. And notice how structured that is. It's not guessing, it's not predicting, it's constructing a valid path through a space of possible states. So in deterministic planning, actions are modeled very precisely. An action is a partial function from states to states. That means it only applies in certain conditions, and when it applies, it produces a well-defined result. Each action has two essential components, preconditions and effects. Preconditions specify when the action can be executed. Effects specify how the state changes after the action is performed. This structure is extremely important. It allows us to reason formally about what actions are allowed and what they will change. Without explicit preconditions and effects, planning becomes vague and unpredictable. So now let's connect this directly to cybersecurity. Every automated response step in a SOAR playbook has preconditions and effects. Preconditions determine when the action is allowed to execute. Effects determine what changes in the effects determine what changes in the system state. Everything else remains unchanged. And this is exactly the strips model. So when a SOAR platform executes a playbook, it is not improvising. It is checking conditions and then applying controlled state transitions. If the conditions hold, the system moves from one well-defined state to another. And automation is not reaction in the emotional sense. It is modeled change under explicit rules. So now let's talk about strips representation. And so now we're going to formalize what we just described conceptually. In the strips representation, a state is modeled as a collection of feature value pairs. Instead of thinking of the world as a large monolithic structure, we break it down into individual properties, things that are either true or false or have specific values. For each action, we explicitly list two things, its preconditions and its effects. Preconditions specify what must be true for the action to execute. Effects specify what becomes true after the action is executed. And here is the key simplifying assumption. Anything not listed in the effects is assumed to remain unchanged. This is known as the frame assumption. It prevents us from having to explicitly state every single property that stays the same after an action. Without that assumption, planning would become unmanageable very quickly. So let's look at a concrete example using the delivery robot. If the robot wants to pick up coffee, it must be at the coffee shop and it must not already be holding coffee. So those are the preconditions. The effect of the action is that the robot now has coffee. Everything else about the world remains unchanged. Similarly, if the robot delivers coffee, it must be at the office and holding coffee. Those are the preconditions for that action. After the action, it no longer has coffee, and Sam no longer wants coffee because he's already received it, and nothing else has changed. So notice how structured this is. There is no ambiguity about when an action applies or what it changes. This precision is what makes automated planning possible. If actions were vaguely defined, there would be no way to reason systematically about sequences of actions. So now we can define the deterministic planning problem formally. We are given three things: a description of actions, an initial state, and a goal condition. The task is to find a sequence of actions that can be executed from the initial state and that results in a state that satisfies the goal. That's it. That's the core problem. It sounds simple, but the difficulty comes from the size of the state space and the number of possible action sequences. Planning is about navigating the space efficiently while respecting the structure defined by preconditions and effects. And now let's talk about forward planning. Forward planning works exactly the way it sounds. We start from the initial state and search forward through the state space. Each node in the search graph represents a possible state. Each edge represents an action that transforms one state into another. An action is applicable only if its preconditions are satisfied in the current state. When we when we apply the action, we generate a new state according to its effects. A plan then is simply a path from the initial state to a state that satisfies the goal condition. Forward planning is intuitive because it mirrors execution. We simulate what happens if we apply actions step by step until the goal becomes true. Now let's connect that concept to cybersecurity practice. When an automated response system detects a compromised host, an active malicious session, or elevated privilege, it doesn't guess what to do. It starts from the current belief state and applies allowed actions. Disable the account, isolate the host, revoke tokens. And in that way, it is moving step by step towards containment. SOAR platforms execute playbooks by traversing reachable states. In other words, automated response is forward search through a structured state space. The system evaluates which actions are allowed, applies their effects, and moves toward a desired secure state. Forward planning is not just an academic idea, it formalizes what response automation already does in practice. Now, when implementing forward planning, we typically do not generate the entire state space in advance. Instead, we construct the search graph on demand. That means we only generate states that are reachable from the initial state by applying valid actions. This matters for efficiency. In realistic problems, the number of theoretically possible states can be enormous. Generating only reachable states keeps the problem tractable. However, as we search, we may encounter the same state more than once through different sequences of actions. That means we need mechanisms like cycle checking or multiple path pruning to avoid redundant work. So forward planning is not just about applying actions, it is also about managing search intelligently. Now, even in deterministic planning, brute force search can become expensive. So we often incorporate heuristics or domain knowledge to guide the search. A heuristic function estimates how far a given state is from achieving the goal. It doesn't need to be perfect, it just needs to provide guidance. We can also prune obviously unhelpful actions. For example, in the delivery robot domain, there is no point picking up coffee if no one wants coffee. That kind of domain-specific pruning reduces unnecessary branching. In practice, intelligent planning is rarely blind. It uses structure, heuristics, and constraints to reduce the search space while still preserving correctness. Now let's talk about regression planning. Regression planning takes a different perspective. Instead of starting from the initial state and searching forward, we begin with the goal condition and work backward. We ask what must be true immediately before this goal can be satisfied. In regression planning, nodes represent sub-goals, partial descriptions of states that must hold. We then identify actions that could achieve one of those sub-goal conditions and compute what must have been true before that action. This continues until we reach a sub-goal that is satisfied by the initial state. At that point, we have effectively constructed a valid plan. Regression planning shifts the focus from reachable states to required conditions. Now think about how this mirrors cybersecurity investigation. When analysts detect data exfiltration or unauthorized access, they don't start from scratch and simulate everything forward. They begin with the observed outcome and ask what conditions had to be true for this to occur. Was there privilege escalation? Were credentials compromised? Was there a misconfiguration? This is regression reasoning. It's backward search over possible preconditions that could explain the observed state. So regression planning is not just an algorithmic alternative to forward planning. It formalizes a system, or rather it formalizes a style of reasoning that analysts use every day. Now, as we search whether forward or backward, we can easily revisit the same state or sub-goal multiple times. Loop detection prevents us from exploring cycles where we return to a state already on the current path, and multiple path pruning prevents us from exploring different paths that lead to the same state when we've already found a simpler or better path. In regression planning, there's an additional idea. If one sub-goal is strictly more complex than another, meaning it contains all the same requirements plus additional ones, then solving the simpler one first is preferable. If we've already reached a simpler sub-goal, we can prune the more complex version. These pruning strategies don't change correctness, they improve efficiency. Without them, planning would quickly become computationally impractical. Now, just as with forward planning, regression planning can also benefit from heuristics and pruning strategies. In regression, we are searching over sub-goals rather than complete states. That means we can estimate how difficult a particular sub-goal might be to satisfy. A heuristic, in this context, estimates how far a sub-goal is from being satisfied by the initial state. We can also eliminate impossible or inconsistent sub-goals early. If a sub-goal requires conditions that cannot logically hold together, there is no need to explore that branch further. The core idea is the same as before. Planning is not just about correctness. It is about managing complexity efficiently while preserving valid solutions. Now let's compare the two approaches directly. Forward planning is driven by the initial state. It explores what is reachable. It is unconstrained by the goal except through heuristics that guide the search. Regression planning is driven by the goal. It explores what must be true. It is unconstrained by the initial state except when we check whether a sub-goal is satisfied. Which approach is more efficient depends on the structure of the problem. If the branching factor is small going forward, forward planning may be preferable. If the goal condition is highly specific and restrictive, regression planning may reduce the search space more effectively. There is no universally superior strategy. The choice depends on the domain and how information is structured. And this distinction has a direct cybersecurity parallel. Attackers move forward. They start from initial access and explore what is reachable. Privilege escalation, persistence, lateral movement, impact. This resembles forward planning. Defenders often reason backward. They begin with protected assets like sensitive data and critical systems and ask what conditions would allow compromise. That resembles regression planning. Planning models both behaviors. In real-world systems, attack path analysis tools simulate forward reachability, while defensive engineering frequently works backward from crown jewels to required controls. Cybersecurity can be understood as the interaction of opposing searches. Now we move to a different formulation of planning. Instead of treating planning purely as search through a state graph, we can encode it as a constraint satisfaction problem. In forward planning, we only consider states that are reachable from the initial state. In regression planning, we only consider states that can lead to the goal. In the CSP formulation, we constrain both simultaneously. We define variables representing states and actions across discrete time steps and impose constraints that enforce initial conditions, action applicability, state transitions, and goal satisfaction. The challenge is that this requires us to fix a planning horizon, the number of time steps we are willing to consider. For each possible horizon, we construct a CSP and attempt to solve it. This reframes planning as structured constraint enforcement rather than incremental graph exploration. And to encode planning as a CSP, we first choose a planning horizon, which we'll call K. This represents the number of time steps in our potential plan. For each time step from 0 to K, we create variables representing each state feature. These variables capture how the state evolves over time. For each time step from 0 to k minus 1, we also create a variable representing the action executed at that time. So instead of thinking about a single state, we are modeling an entire sequence of states and actions simultaneously. Once we define these variables, we can add constraints that enforce preconditions, effects, frame assumptions, the initial state, and the goal state. If the CSP has a solution, that solution corresponds to a valid plan. Now let's look at what this encoding actually looks like in a simple example. In the delivery robot domain, once we choose a planning horizon, say 2 time steps, we create state variables for each feature at time 0, time 1, and time 2. We also create action variables for time 0 and time 1. Instead of searching forward step by step, we now describe the entire plan at once. We are asking, is there an assignment to all of these variables that satisfies the constraints? If such an assignment exists, then the sequence of action variables across time steps constitutes a valid plan. The key idea here is that we have transformed a sequential search problem into a global constraint problem over time-indexed variables. And once we define the variables, we impose constraints that enforce the logic of planning. Precondition constraints ensure that an action at time t is allowed only if the required state conditions hold at time t. Effect constraints ensure that if an action occurs at time t, the resulting state at time t plus 1 represents the action's effects. Frame constraints enforce that anything not changed by the action remains the same from one time step to the next. We also add initial state constraints at time 0 and goal constraints at the final time step. Together, these constraints guarantee that any satisfying assignment corresponds to a valid plan under the deterministic model. Now let's connect this to real-world automation. Automated systems do not act freely. They operate under policy constraints, compliance requirements, operational limits, and risk tolerance. When we encode planning as a CSP, we are explicitly modeling what actions are permitted, what states are valid, and what must remain unchanged. In practice, automated response engines enforce constraints before executing actions. If a required condition does not hold, the action is not allowed to proceed. So planning as CSP is not just a theoretical formulation. It reflects how constrained decision-making operates in structured cybersecurity environments. Security automation is not arbitrary action. It is constrained reasoning over state transitions. And that concludes the lecture on Chapter 6.